Greetings, this is Professor Roman. Let's continue our discussion of linear algebra. We've been studying inner product spaces, and we finished in the last lecture with the issue of when a subspace S of an inner product space V has an orthogonal direct complement. So let's say S is a subspace of V. We do know that S perp, the orthogonal complement of S, always exists. It's simply the set of all vectors that are orthogonal to everything in S. It's non-empty because the zero vector belongs to S perp. Therefore, and also we know that S and S perp are essentially disjoint. I left that for you as an exercise. Therefore, the orthogonal direct sum S, orthogonal direct sum S perp exists. The question is this equal to V? We saw an example where it was not. In fact, for little l2 and the subspace consisting of the sequences in little l2 with finite support, we saw that S perp is in fact trivial. And so S orthogonal direct sum S perp is just S itself, which is a proper subspace of V. And that's where we left off. Oh, I also mentioned that we are going to show that if the subspace S is finite dimensional, then it does have an orthogonal direct complement. And we did see that if a subspace has an orthogonal direct complement, that orthogonal direct complement is the orthogonal complement of S. So that's where we left off. An earlier theorem, one that we discussed last time, Theorem 5.28, says that any vector V in the span of an orthonormal set O of vectors, this is in a vector, obviously in an inner product space, has a very nice representation. V, we know, is a linear combination of the vectors in O, because we're assuming V is in the span of O. And so it is a linear combination. Let's say O, I should have probably said O equals U1 up through UM here. Okay. This is what the expansion looks like. The point here is that the coefficients in the expansion are very easy to, at least in theory, to compute. They're simply the inner product of the vector we're representing with each of the vectors in the orthonormal set. When O is a finite set, even if V is not in the span of O, we can still write this linear combination. Nothing stopping us. It will not equal V unless V is in the span, but it's still a vector in the inner product space. The question is, how does this vector relate to V when V is not in the span of O? Here's a picture. Here is the subspace spanned by O, and I'll call it S for convenience. Here is a vector V that does not lie in the span of O. In other words, it doesn't lie in the subspace S. This vector, which is rewritten here, okay, is denoted by v hat, oftentimes, or another notation that we will use is rho sub s perp of v. It is called the orthogonal projection of v onto the subspace S. And this is the picture. Here is v, and here is v hat. And this belongs to the subspace S. This is the orthogonal projection. Of course, if v is in S, then the orthogonal projection v hat is equal to v. Otherwise, it is not. This vector v hat is also called the Fourier expansion of v with respect to the orthonormal set O. And each of the coefficients in this expansion is called a Fourier coefficient. The difference, v minus v hat, let me get the picture back. That's this vector here. This is a parallelogram. Is called the residual vector for v with respect to O. So we have the orthogonal projection and we have the residual vector. The sum of these two is the original vector v. V hat is, as you probably guessed, rather important. It is the unique vector in S for which the residual vector is orthogonal to the subspace. So v minus v hat is orthogonal to S, just as this picture would indicate. Obviously, a picture is not a proof. This picture is the support for the statements of the theorem. So there's only one vector in S for which the residual vector v minus that vector is orthogonal to S, and it is the orthogonal projection. So this orthogonal projection, therefore, once we've proven this, of course, therefore we can say that the orthogonal projection does not depend on the choice of orthogonal basis. Okay. This should really be orthonormal. We could do this for orthogonal sets, but it's simpler just to normalize, non-zero, just to normalize all the vectors. Orthonormal basis for S. Okay. As I mentioned a minute ago, we have V is the sum of its orthogonal projection and its residual vector. The orthogonal projection belongs to S. The residual vector belongs to S perp. And since V was an arbitrary vector in the inner product space, we have this orthogonal direct sum, which we know exists, is actually equal to V. And this is what I mentioned at the end of last time we were going to show And we'll return to this again, and we'll single it out as a separate theorem. But what we have, what this statement of this theorem implies, once it's proved, is that if S is finite dimensional, has a finite orthonormal basis, then in fact, even if V is infinite dimensional, S perp, the orthogonal complement of S, is the orthogonal direct complement of S. This vector V hat, the orthogonal projection, is the best approximation to V from within S. Now what that means by best approximation is that V hat is the unique vector, say little s in capital S, that is closest to V in the metric, the distance function, induced by the inner product. And that looks like this. This is the distance from V to V hat that is less than the distance from V to S for all other vectors, little s in capital S. So in the picture, here's another vector, little s. This vector is farther away from V than V hat is. V hat is the closest vector in S to V. Best approximation. There's a famous inequality associated with this called Bohls Inequality, and that says that the norm of V hat must be less than or equal to the norm of V. They are equal if and only if V is equal to V hat, or put another way, if and only if V belongs to the subspace S. So by taking orthogonal projection, we cannot increase length. Other types of projections can increase the length of a vector. Orthogonal projections do not. As to part one, as to the fact that V hat is the unique vector in S for which the residual vector is orthogonal to S, every vector in S is a linear combination of the u sub i's, the orthonormal basis for S. Now, if V minus S, so S belongs to capital S, V minus S will be orthogonal to the subspace S if and only if it is orthogonal to every basis vector for S. And that's equivalent to saying that the inner product of V and uj is equal to the inner product of S and uj for all j, 1 through m. But the inner product of S and uj, we've been through this before, when you take the inner product of this sum with uj, the only term that survives is the jth term, and uj is 1 because we're dealing with orthonormal vectors, and so we just get a sub j. So in summary, V minus S is orthogonal to the subspace S if and only if the inner product of V with each basis vector uj is this coefficient aj in S. So this holds if and only if S is equal to this sum, which is in fact V hat by definition. So V minus little s is orthogonal to the subspace if and only if little s is V hat. And that proves part one. For part two, if little s belongs to capital S, let's see what part two says. This is what V hat is the best approximation to V. It's the closest vector 2v from within the subspace. So if S is in the subspace, v hat minus S then belongs to S, because v hat belongs to S, little s belongs to S, and that implies that v hat minus S is orthogonal to the residual vector. We've just proven that the residual vector is orthogonal to the subspace S. So we can apply the Pythagorean theorem to these two orthogonal vectors. V minus S, norm squared. Here I've subtracted v hat and added v hat, so I haven't done anything. But these two vectors are orthogonal, so the norm squared is the square of the norms added together. So when is this the smallest possible value for which little s? This doesn't involve little s, only this one. So this will be smallest, and therefore the norm of v minus s will be smallest, when s equals v hat, and only when s equals v hat. And that is this expression here. When s equals v hat, these are equal. When s is not v hat, this is a strict inequality because of this extra term. And I'm going to leave the proof of Bohls inequality as an exercise for good practice. So this is a very important theorem in not only in theory but in practice, as we will see. I should make a remark about the notation. The notation v hat is quite common, but it's not the best notation because it doesn't identify the subspace S, and a change of subspace will change the orthogonal projections. It shouldn't be surprising. We did show that it doesn't matter what orthonormal basis you pick for S, but it still depends on S. So this notation, which may not be as common, is at least very descriptive. It's complete in its description. I think other books will use other notations that are similar to this. But this has all the features we want. It gives the subspace. It says it's an orthogonal. And rho is used for projection, so it's an orthogonal projection. And of course, of v, of the vector v. So this is, I think, preferred notation, even though it's a lot more complicated. So, as I said a moment ago, we're going to single out one fact from this last theorem. We've seen from an example given last time that if S is a subspace of an inner product space V, then this, let's write this here, then this is not necessarily the case. The orthogonal direct sum exists, but it may not equal V. What we have just shown, and by the way, in that example, the subspace S was infinite dimensional. The subspace of all sequences, square summable sequences with finite support. But what we have just shown in this previous theorem is that if S is finite dimensional, then this does hold. And this is called the projection theorem. Let V be an inner product space. If S is a finite dimensional subspace of V, then V equals S orthogonal direct sum S perp. And so in particular, a vector little v can be written as v hat plus v minus v hat, which is in this orthogonal direct sum. So we get the components of V by taking V hat, the orthogonal projection is the component, the S component, and the residual vector is the S perp component of V. If V is also finite dimensional, not just S but V itself, then this orthogonal direct sum will allow us to write this. The dimension of V is the dimension of S plus the dimension of S perp. Or perhaps more useful, this tells us the dimension of S perp is the dimension of V minus the dimension of S, which is the codimension of S. I should mention that in my experience looking at other books, many times the projection theorem will be stated only for finite dimensional interproduct spaces. There's no reason to do that unless the author is afraid that the readers will be confused or have a harder time remembering the theorem. The key point of the projection theorem is not that V is finite dimensional, but that the subspace S is finite dimensional. The projection theorem has a variety of uses. Theorems that have a name generally do have a variety of uses. They're particularly important since they're given names. Or I should say the other way around. They're given names because they are particularly important. Here's an example. Let S be a finite dimensional subspace of an interproduct space V. Then the double perp of S is equal to itself. This can fail if S is infinite dimensional. How does one understand the double perp? Well, S perp is the set of all vectors orthogonal to S. So this is the set of all vectors that are orthogonal to all the vectors that are orthogonal to S. That is probably something you'll have to ponder a little bit. But remember what happened with our example of last time. V was L2 and S was the square summable sequences of finite support. S perp was trivial. And so what is S double perp? It's all the vectors that are orthogonal to the trivial subspace, or in other words, to the zero vector. Everything is orthogonal to the zero vector. So in that case, S double perp was all of V, much bigger than S. Okay. So again, this applies only under the hypotheses of the projection theorem, namely that S is finite dimensional. Proof is very short, and I think what you should do is stop the video and see if you can do this proof yourself. If not, then look at this. Now let's take a look at an important application of the projection theorem. Consider a system of equations, AX equals V, where A is an M by N matrix, and so linear map from Fn to Fm. This system has a solution, that is, it's consistent system, if and only if V belongs to the image of A. But what do we do if V does not belong to the image of A? This can easily happen if we're modeling some physical phenomenon and there are errors in measurement, and we end up with a constant vector on the right side here that has an error in it, and so this system is inconsistent. Well, what we would like to do is find a consistent system that best models the original inconsistent system. And this system, the consistent system, is going to be AX equals V hat, where V hat is the orthogonal projection. If we look here, here is the image of A, and here is V. This is an inconsistent system. V hat is the orthogonal projection of V onto the image of A, and since V hat is in the image of A, this system is consistent and has a solution, and it best models the original system because V hat is the vector within the image of A that's closest to V. This system is called the least squares system associated with the original system AX equals V, and any solution to this system is called a least squares solution to the original system AX equals V. So a least squares solution to this system AX equals V is a vector S for which AS is closest to V among all the vectors in the image of A. Or put another way, for which the residual vector V minus AS has smallest possible norm. I guess I should just say smallest norm. And it's important to note that if S is any particular least squares solution to the original system AX equals V, in other words, a solution to AX equals V hat, then all of the least squares solutions are the set of all least squares solutions is the coset S plus the kernel of A. This just follows from elementary theory of systems of linear equations, the relationship between a solution to a non-homogeneous system and the solutions to the homogeneous system. Now, if a vector W is a least squares solution to AX equals V if and only if AW equals V hat, and this is equivalent by an earlier theorem to the statement that the residual vector AW minus V is orthogonal to the subspace. We used to call it S, but here it's the image of A. V hat is the unique vector for which V hat minus V is orthogonal to the subspace upon which we are projecting. Now I'm going to leave it as an exercise for you to show that the image of A perp is equal to the kernel of the adjoint A star. And therefore, this statement is equivalent to the fact that W satisfies this equation. And that can be written this way, and this is the equation. So a vector W is a least squares solution to AX equals V if and only if it's a solution to this system. The equations in this system are called the normal equations for the system AX equals V. So we just have to solve the normal equations to get the least squares solutions, and I'll show you an example relatively soon. But first, among all the least squares solutions to a system AX equals V, the most interesting one is the solution of minimum norm, say M, which, if it exists, and we will show that it does, must be unique. To see that there must be unique, if we had two solutions, two distinct least square solutions, S and T, of minimum norm, then this vector, S plus T over 2, would also be a least square solution, and the triangle inequality would tell us this. The norm of S plus T over 2 is less than or equal to 1/2 the norm of S plus the norm of T, which is equal to M. But strict inequality cannot hold here, because then this least squares solution would have norm less than M, which is impossible. So S and T have to be scalar multiples of one another. But since they have the same norm, then one has to be the negative of the other. That tells us that 0 is a least squares solution, and so V hat is 0, and that would imply that 0 is the unique least squares solution of minimum norm, and so that contradicts the fact that we have two distinct least squares solutions. So the least squares solution of minimum norm is unique if it exists. Now, if S is any least squares solution to AX equals V, then the previous theorem tells us that the least squares solutions are precisely the vectors in this coset. Is that the theorem that told us that? Yeah. So, we have to search for a necessarily unique vector of minimum norm in this coset. But because the kernel of A is finite dimensional, the projection theorem allows us to decompose Fn, which is the domain of the map A, this way. And so a least squares solution can be decomposed into a sum S1 plus S2, where S1 is in the kernel of A and S2 is in kernel of A perp. And then V hat, which is AS, because S is a least squares solution, is equal to A times S1 plus S2, but S1 is in the kernel of A, so this is just AS2. So S2, which belongs to the kernel of A perp, is also a least squares solution. And being a projection, an orthogonal projection, its norm cannot be bigger than the norm of S. So, for every least squares solution S, its orthogonal projection, which I'll call T sub S, onto kernel of A perp is also a least squares solution whose norm is at most the norm of S. So if we're looking for a least squares solution of minimum norm, we can just concentrate on the projections, on the orthogonal projections of all of the least squares solutions. In other words, we just have to look in this intersection, which I call I. these are the least square solutions, and so the intersection are the least square solutions that belong to kernel of A perp. The orthogonal projections of all the least square solutions. In here is where we must find a vector of minimum norm. And that will be our least square solution of minimum norm. So we need to look at this set, this intersection. Well, if we have two members of I, s plus x and s plus y, so x and y both belong to the kernel of A, then the difference between these two vectors, x minus y, belongs to the kernel of A. When you take the difference of two cosets here, you get something, or two members of this coset, you get a member of the kernel of A. But kernel of A perp is a subspace, and so the difference is also in the kernel of A perp. So this difference belongs to both of these subspaces, but they are essentially disjoint, so the difference is 0, and x equals y. In other words, all of the projections T sub s, as S ranges over the least square solutions, are the same vector. You get the same vector no matter which least square solution you project onto kernel of A perp. In other words, this intersection I is just a singleton set, one vector. It's the vector you get by projecting any least square solution onto kernel of A perp. So this vector T is the unique least square solution of minimum norm. I'll add the word unique here. Summary. The least square solutions to Ax equals b are the solutions to the normal equation. There is exactly one least square solution T to this system that lies in the kernel of A perp. And this solution is the least square solution of minimum norm. Again, I'll put unique. And in fact, T is the orthogonal projection of any least square solution onto the subspace kernel of A perp. Now it's time for examples. Here is a system, 3 equations and 2 unknowns. This is the matrix of coefficients. This is its adjoint. We need this product to create the normal equations, which look like this. And this side can be simplified. This system has only one solution. So it is the least square solution. It's the only least square solution to this system, which is inconsistent. And therefore, of course, it's the least square solution of minimum norm. Let's consider this system where A is given by this matrix and V is given by this matrix. Compute the adjoint, the normal equations, solve them. These are the least square solutions to the original system. If we want to find one of minimum norm, we've actually got two choices. We can just proceed directly. The norm squared of this vector, z is a parameter here, is given by this, which is a quadratic in the parameter z, and we can just find the value of z that gives a minimum least squares solution. That's z equals 11/6. So the unique least squares solution of minimum norm is this one. Alternatively, we can look for a least squares solution within the kernel of a perp. So here's the kernel of A. It's spanned by this single vector, and so an arbitrary least squares solution belongs to the kernel of a perp if and only if it is orthogonal to this vector, 1, -1, -1. That's this equation. And this holds if and only if this holds. This is just a linear equation in z, and its solution is z equals 11/6. Let's consider an important use for least squares systems and least squares solutions. So let's imagine a physical device of some sort. And for each real input x, the device outputs a real number L of x. And suppose that theory indicates that this output function should be more or less linear. So it should have the form L of x equals c plus dx. To find this linear function, L of x, that best models the device, we plot a large number of points in the plane. The inputs are AI, the outputs are BI. So here's a picture showing 4 points. Now it seems reasonable that the graph of this best approximating line should be the line that best fits the data somehow, and by this we mean that the sum of the squares, should be parentheses here, the sum of the squares of the vertical errors, that's the lengths of these lines, should be as small as possible. There are alternatives to this. This number here is called the least squares error, and the line L is that minimizes the least squared error is called the least squares line. But there are other possibilities. We could just take the sum of the absolute values. But absolute values are more difficult to work with algebraically, so it's customary to just square these errors and minimize the sum of the squares. The least squares error, E, actually can be written in a different form as the norm squared of a vector that looks like this, ax minus v. So we set A equal to this matrix. We're going to assume that the AIs are distinct, which is not a problem. We'll put in distinct inputs. X is this matrix CD. These are the coefficients in the equation for the line L, and these are the outputs. So AX minus V looks like this, and these are precisely the entries here. So E is in fact equal to the norm squared of AX minus V. And so to minimize E, we need to minimize this norm. But that's exactly the purpose of a least squares solution to this system. It minimizes this norm. So to put it together, consider a set of at least 2 data points in the plane where the inputs are distinct. The least squares line that best approximates the data in the sense of least squares error is given by the unique least squares solution to this system. All that's missing, well, all it's missing here is that the uniqueness. We have to prove that the least squares solution to this system is unique. But this matrix A of coefficients in the system has rank 2 because we're assuming the AIs are distinct. And since A maps R2 to Rn, it's injective. And so any system, including the least square system, if it has a solution, which it does, that solution must be unique. So here's an example. I have 4 data points. Here is the appropriate equation. I place the inputs in the second column here and the outputs over here. These are the normal equations for the system. This is the unique solution, so this is the least squares line. I found a program on the internet that graphs least squares lines, and so I plugged in those data points, and this is the picture I got, and here is the equation of the line, which is the same as what we have here.